So today we're going to be looking at um, derivatives of trig functions. So before we start, just a few reminders. If you have not yet done your trig review sheet notes, I would strongly suggest going through and looking at those. If you haven't, you'll still be able to follow your way through, but it would be helpful to be able to do that. So just a few reminders. Tangent is sine over cosine. We have our three reciprocal functions. We have cosecant, secant, and cotangent, and those are the reciprocals of our three primary trig ratios. We also know that if we have something like sine squared x, that's the same as writing sine x all squared. Also, a reminder, sine x over x, those x's cannot cancel out. And if we have sine x times x, this is not sine x squared. This is the same as saying x times sine x. So just some notation issues. Also, if you have sine and then a cosine x inside, you cannot distribute that sine inside. This means that you have a cosine x value that has all been plugged into sine. Okay. Also, a reminder that pi radians is 180 degrees. So this first page, we're just going to be going through and finding out why the derivatives of sine and cosine are what they are. You will not need to replicate these diagrams, but this is just so that you're not taking my word for it and you can actually see how they're developed. So just a reminder, our graph of sine x has a maximum of 1 and a minimum of -1. And it starts at the origin. It increases and has a maximum at pi over 2. It goes back down to the x-axis when our angle is pi. It then goes down to a minimum at 3 pi over 2 and back up to our axis at 2 pi. And so one cycle of sine looks like this. We can go in the opposite direction as well, where we cross at negative pi and negative 2 pi. Our minimum would be at negative pi over 2 and our maximum at 3 pi over 2. And this would show us two cycles of sine. If we want to graph cosine, we could go through a similar motion. So just a reminder that if I have a tangent line, if I want to graph the derivative y prime, okay, I'd be graphing all my y prime values with their corresponding x values like we've done for other functions so far. And if we had tangent lines at any of our peaks or any of our valleys, we drew tangent lines on all of these peaks and valleys, the maximums and minimums. These would have slopes of 0. What that means is y prime is 0 at x equals negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, etc. So we can put a y value of 0 on our graph of our derivative at all these pi over 2 values. We also could see that we have positive slopes here, okay, here, and here. And at each of these pi values, our slopes are actually 1. Okay. And we could calculate that using our definition of a derivative at those x values, okay, if we wanted to. So on the y-axis, we have a slope of 1. I should probably actually label my y-axis here. At negative 2 pi, I have a slope of 1. And at 2 pi, I have a slope of 1. And in between, we can see that we have negative slopes at pi and negative pi. And our slopes there are actually -1. Again, if we wanted to calculate that exactly, if you didn't want to take my word for it, you could use definition of a derivative to do so. but then you would need your trig identities from your formula sheet from Math 12 that we also used in our review chapter because you would end up with some identities. Okay. So at negative pi and pi, we have y values of -1. And then we can draw this in here. And what does this graph look like? What do we notice about the graph of the derivative? Well, it's the graph of cosine. What this means is that if y is equal to sine x, y prime is cosine x, or in other words, the derivative of sine is cosine. We can repeat the same sort of process to find the derivative of cosine. So again, we know that the cosine graph looks like this. Again, if you didn't do your trig review, that might be a little harder to remember. And we can go the other direction as well. Remember, our period is 2 pi. For a cosine, we start at the maximum. Halfway through the period, we reach the minimum, and then we return back up to our maximum. And if we repeat the same process we just did for sine, we can see that at all of the peaks and valleys, we have a slope of 0. So at -2 pi, -pi, 0, pi, and 2 pi, y prime is 0. Okay. We can see that we have two spots where we have positive slopes here. So at -pi/2 and 3 pi/2, our slope is 1. Again, we could calculate that exactly using definition of a derivative, but we would need our trig formula sheet, our sum identity, and we could evaluate at either of those x values. So again, I need to label my y-axis here. And we know that at -pi/2, we have a slope of 1, and at 3 pi/2. And we have a bunch of places with negative slopes here. They would continue as well. And again, slope here would be -1. And if I connect these, kind of looks like a sine graph, but upside down. So this, my graph of my derivative, so reflection of a sine graph. What this means is that if we have y equals cosine x, then y prime is actually equal to negative sine x. Because if we have a reflection of a sine graph, I guess I should be specific, a vertical reflection of a sine graph, that would be negative sine x. So just a reminder, sine x looks like this. Negative sine x looks like this. Okay. So again, you do not need to be able to replicate these graphs, but you will need to know that the derivative of sine is cosine and the derivative of cosine is negative sine. Okay. So we're going to try finding some derivatives. Okay. So I'm going to write at the top for our use, the derivative of sine is cosine, and the derivative of cosine is negative sine. All of our other derivative rules will still apply: product rule, quotient rule, constant multiple rule, etc. So this first one that we were being asked to differentiate, we can use constant multiple rules. So again, if we actually write out the whole rule, this would be the same as saying if I want to do the derivative of f of x, this is the same as saying 3 times the derivative of sine x minus 4 times the derivative of cosine x. And what that means is f prime is equal to 3 times cosine x minus 4 times negative sine x. Remember, this is not 4 minus sine x. This is 4 times negative sine x, which would give us 3 cosine x plus 4 sine x. Again, many of you will just go straight to this answer. You do not need to write this first line of work. This first line of work here is not necessary every time we do these constant multiple questions. The next one, you'll see that it looks like we have two separate functions. We have x squared and cosine x. The x squared is like our f. The cosine x can be like another function g, and they are multiplying together. This tells me I need product rule. So remember, we said that for product rule, and if you tried some practice questions, you would see that for product rule, you cannot always expand it and make it any easier. This is an example of that. So if I want to find y prime, I need to do the derivative of the first thing, which is 2x, times the second thing, which is cosine, plus the derivative of the second thing, the derivative of cosine is negative sine, times by the first thing. Now, again, we can't simplify this at all, but we should rewrite this second bit here. Remember, on the front page, it tells us this is not good notation. So we're going to rewrite this as 2x cosine x. We can change this to minus x squared sine x. Okay. If you want, you can factor out an x here because there's an x in both terms, but you do not have to. If you do that, you get x times 2 cosine x minus x sine x. Either one is fine. So we're going to do one more question here. Find the equation of the tangent line. So we need y equals mx plus b. Recall that m is your slope of your tangent line. And this is the same as saying f prime of x. So we can use quotient rule. Okay. We're looking for y prime so that we can find our slope. Our derivative of the top is 0. Our derivative of the bottom is sine x plus cosine x minus the derivative of the bottom. So the derivative of the bottom, the derivative of sine is cosine. The derivative of cosine is negative sine times the top all over the bottom squared. And then we can simplify this. Okay, so remember your quotient rule is y prime equals f prime g minus g prime f all over g squared. And in this case, f is 1 and g is sine x plus cosine x. So what this gives us is our first term is 0 times a bunch of stuff, so that's just 0. And then the second one, we can distribute this negative into the brackets. The 1 we don't need to do anything with here. So we get negative cosine x plus sine x all over sine x plus cosine x squared. Now we're at a specific point. Y prime is going to be the 0 we don't need, negative cosine of 0 plus sine of 0 all over sine of 0 plus cosine of 0 squared. Remember that cosine of 0 is 1, sine of 0 is 0. So this one we're not going to need anymore, and this one we're not going to need anymore. So we end up with negative 1 over 1 squared, which is negative 1. This is our slope, our m. Okay. Now we know we're trying to find y equals mx plus b, our equation of our tangent line. We know that y is 1, our m is negative 1, our x is 0, plus b. This means b is 1. And our tangent line equation is therefore y equals negative x plus 1. Okay. Again, at the bottom of our notes, you'll see some practice questions, just a few from your 5th edition today. And we will continue doing some more of these derivatives tomorrow.